Ah, no. So, the response terminology. A circuit's response can be either source dependent or time dependent. So, these are two different ways of looking at sources, at responses. So, source dependence means we're going to look at the response due to different sources. So, a natural response is essentially what the response is if you have no sources or an absence of sources. So, the way I like to look at this one mathematically, I look at this as a differential equation where I'm given an initial condition of 0. So the natural response is saying, essentially, if I have a circuit and I pull out the battery real fast, immediately once I pull out that battery and there's no power sources, there's no sources there, what happens to the circuit? How does that circuit die down? Or, in reverse, if I immediately plug a circuit in, what does that source do as it charges up? So that's the first, but that's the natural response. It's, um, the fixed response, I believe it's also sometimes called. Then we also have the forced response, and so this is response due to external sources. So this is a response that comes from an initial condition of something other than 0. So you can give initial conditions of a step function coming into it, or a ramp function, or some other interesting equation function. And for source dependence, we get the complete response by adding the natural response plus the forced response. So if I look at these in a very simple way, uh, usually and often you'll see the natural response might just be a constant. So that might just be 3 or 5 or something like that. Or the forced response might be some kind of equation with variables in it. So if you look at the combination of the two, the natural response, which is where the essentially your function starts at, plus your forced response, which is whatever's changing due to the different conditions, is going to give you this complete response. And mathematically, we're going to look at the differential equations that are going to solve out for that complete response for a source dependence. Now, the other way to look at these circuits is through time dependence. And time dependence is, again, it's an interesting way of looking at them. We got two different parts. We've got a transient response and a steady state response. So transient response means that the response is time varying, so it's temporary. So look at like um, an exponential curve. If you plot that, it varies versus time, and there's no pattern there. There's no solid line that goes across. There's no prediction of something leveling out to 0. Essentially, you're just having an increase. Or you can have random signals in there too. So that's your transient response. Time changing. Transient is change. So time changing response. Versus your steady state response. So this is a time independent or a periodic response. So a sine wave, even though it is changing, a sine wave has a very predictable response. It has the same amplitude. It has the same period. So that waveform up and down, you can kind of consider, and you do consider it as a steady state response, just like you would as a normal line. Like if I plug 3 volts into a circuit, that 3 volts is a 3-volt response. It stays 3 volts all the way from 0, time equals 0 when you plug it in, to as long as it continues out. The periodic response is like an alternating current response. So if I plug some electrical component into an alternating current outlet, that's also, even though it's changing periodically, and the periodic change is um, being able to be written by a sine function that's predictable at any given time. We know exactly where that is. So the complete response for time dependence is the addition of the transient response plus the steady state response. And you're going to see that in the differential equations we look at coming up too. So the natural response of a charged capacitor, and this is again one of the more traditional, this is an RC circuit, and this is one of the traditional ways of looking at these circuits so that you can kind of see what's going on and why we're talking about these two different parts. So in the top left hand we have a picture A, which is the RC circuit. And you'll see we leave this on for a while because that's going to charge up the capacitor. So A is any time before that switch is switched from gate pull or pull throw 1 or section 1 dot 1 to dot 2. Right now that circuit is at steady state. It's charged up the entire way, that capacitor. That capacitor is full. And as that capacitor increases its charge, the current that flows through it decreases, because once a capacitor is fully charged, no current is flowing. And so we're going to presume that this has been charged up for a really long period of time, so that capacitor is totally charged. So then we're going to look at state B at time equals 0 or less than 0. At time equals less than 0, this is exactly what I just said. This circuit B is showing that we have a power source Vs, and that's going to go through two different resistors through the switch, and nothing's going to happen. It's going to be an open circuit at the capacitor because this capacitor is fully charged. The current going through it is 0 at that point. That means that entire top line is a supernode with the same voltage as your source. Because remember, there's no current flowing through it, so it all has the same voltage. So if that voltage source is 9 volts, any point above that capacitor on that top line of picture B is going to be whatever that voltage is. 9-volt source, 9 volts up there. And that's an open circuit right there. There's no current flowing through. However, at t equals 0 and greater than 0, we're going to switch that switch and hold it. So at t equals 0, we switch it, and then it stays switched. And that goes to switch 2, which is picture C. And now we look at it. So now we have a charged capacitor up there, and we have a resistor right behind it, and then goes to the negative of the charged capacitor. So essentially that capacitor is going to be providing voltage because it's not instantaneous. It's a function of the capacitor and the resistor. And so this is going to slowly empty the capacitor out, depending on the resistor's value. So different resistors value will allow you to change this differently. In general, the lower the resistor value, so the smaller the resistor value, the faster this will happen. Because if there's just a wire there and there's no resistor, that charge is going to immediately flow from the positive to the negative through those wires. You're going to get a spark and it's going to be discharged. Now, if you have a really, really high resistor value in there, that current is going to flow very slowly through that resistor, and the charge is slowly going to flow because remember, current is charge the flow of charge over time through the circuit. So that's going to give us a very slow flow through there. And so that's how we can solve for V. Now we're going to look at essentially what the equation is, the differential equation for this. So for t equals greater than 0, so at time is greater than a 0, we're going to do KVL in the loop. Because again, it's one loop, so we can apply KVL. Kirchhoff's voltage law, the change of voltages over the individual parts. So if we remember V equals IR, so that's where we get the RI, and then V is going to be the voltage drop of the capacitor. So we can substitute in and plug in our values where I is the current through it and V is the voltage across the capacitor. And the equation for that, I equals C dV dt, or the derivative of current voltage versus time. We can plug that in, R equals C dV dt. So you see how we've plugged that in for the I in the resistor because they're connected. The current flowing out back through the resistor from the capacitor. They're two in the same. They're together now. And so we can solve that out, and without sources, so we're looking at the natural response again. There's no sources in this. We've taken all the batteries out. We're going to look at this natural discharge of power from the capacitor. And that's, again, the natural response. There's no active power adding current anywhere to the system. It's going to just slowly die down. And so we can solve that out where A equals 1 over RC. And that's going to give us our individual values to be able to calculate out what this natural response is. And so we're going to look at here the solution to the first order differential equation. And how we're going to do this is the standard procedure for solving starts by multiplying both sides by EA of t. And this is all from differential equations that you've had before. Actually, we touch on it a little bit in Calc 3. We used to, at least, and then you usually get this, again, heavier differential equations, because it's first-order differential equation. We use the traditional methods of solving first-order differential equations by the multiplying of E up AT, and we can solve through that, and that's going to essentially give us d dt voltage E up AT equals 0, and you can think of that logically. Again, you're going to have essentially you're going to have power being removed through that capacitor. You're going to be losing power out of the system. Current is going to be dropping. The voltage is going to be dropping. And when we integrate both sides of that, we're going to be able to solve out to be able to get Vt E up At minus V of 0, which is your initial condition. And you're going to be able to solve through that V of 0 E up minus T over Rc for any time greater than 0. So that is the solution for the first order differential equation. And from that, we can use that as the natural response solution, sometimes it's referred to. And another thing to notice in here is tau is going to be the time constant of the circuit. And tau equals R times C. And we're going to look at what that means for the circuit. But essentially, you're going to use, you can think of it as almost a percentage of time versus your time constant. Your time, negative time over your time constant. And the time constant comes out of R times C. And so this is going to be your natural response to these circuits given a V of 0 to begin with. And that's essentially showing how your capacitor discharges throughout the circuit. And if you just visually graph this, if you think of E up minus T over tau, and both of those R and C are defined, so it's a constant, it's minus T over a constant, that's going to be what? It's going to look like an exponential decreasing. So that's exactly what you would expect to think from a circuit where your the current is being provided by your capacitor. So here we're going to look at that exactly what I was saying from a visualization standpoint. If we look at A all the way up into 0, this is a graph of the voltage, but all the way to 0, your voltage is whatever your source is. Because remember, if you have a 9-volt source, you have an open circuit at the other side where the capacitor is. So it's always going to be 9 volts at the top. You have nothing removing and no current is flowing through that capacitor, so it just stays 9 volts. But as soon as you switch that switch at time equals 0, you're going to start slowly draining that capacitor, and the voltage is going to start slowly decreasing. And the rate that it decreases is going to be your natural response of that. And that's the equation we just looked at in the previous slide to be able to look at how that response increases. And so as you go out to infinite t, you're going to get closer and closer to 0 because that capacitor is going to be drained closer to nothing. And this is going to be on a decreasing exponential slope because remember, we had that E up minus t over RC. So that's going to give us our decreasing slope as well, or decreasing exponential as well. So interestingly, we're going to look at then just logically what happens when we have current after that. So if you have that same circuit before 0, so at any time before you throw the switch, remember you have an open circuit there. An open circuit means you have no current flowing. No current flowing means 0. So that's why you have a 0 all the way from negative infinity of time to 0. Now, immediately when you throw that switch, you're going to get a step all the way down, an impulse all the way down to your minus Vs of t. And then your current is slowly going to decrease back to 0. So remember, it's negative because the capacitor is charged in the opposite direction of the battery. The positive side of the battery faces the positive side of the capacitor. So when you remove that battery and you flip the switch, that charge is going to go in the exact opposite direction, which is why you're getting the negative there. You got current flow in the opposite direction of the circuit. And so this current flow is going to go from opposite, so not minus 9, if you have already charged the capacitor to 9 volts, minus 9 all the way back up to 0, and that's why it's slowly increasing exponentially. And we can look at the equation for that over in the blue box on the right, and this essentially the derivation for that equation if you want to look through it. It's also in the book, and I can show some examples of it as well. But the derivation for that differential equation, I of t equals minus Vs over R E up minus t over tau, where again, tau is still R times C. So that's just a way of shortening that. Those essentially come out to be a constant because they're defined by single values. And you can see the negative sign, of course, is because the current is flowing in the opposite direction. You're quickly switching the switch, and the current is flowing from that thing that charged all the way backwards through the opposite direction through the resistor. Negative to negative, negative to flip directions of the current flow. That's how I think of it. And now we're also going to look down at power. So if you think about power conceptually through a resistor, P equals IV, you know it's a function of voltage and current. And so our power beforehand, at any time before the switch is thrown at 0, is going to be equal to 0. Because, again, you have no current flowing, If you have no current flowing, 0 times whatever you got for your voltage is going to be 0. And that's how we get 0 power. And so power equals current times voltage. If we look on the right-hand side by the equations underneath the blue box there, we're going to be able to take the equation for the natural response of I of t and multiply it by the natural response of v of t. And those two multiplied out are going to be equal to minus v squared over r e up minus 2t divided by tau, where again tau is RC. And you're going to be able to calculate out from that your power at any given time. So anytime before 0, again, we have 0. That's easy. Immediately, though, when you flip that switch, that capacitor is fully charged. That's going to try to throw as much as current as possible. The current's going to move really fast through that capacitor, through that resistor. And as the charge gets lower, there's less forcing that charge. There's less forcing that current through the resistor, and also there's less voltage because again, voltage is pushing on that circuit. So as both of those die, your power is going to die. So if you're going to blow the resistor because you threw too much power through it, that's going to happen immediately when you throw the switch. If that doesn't happen immediately when you throw the switch, you're slowly going to get less and less power all the way back to whatever your time is that you're looking at, where there's almost no power being consumed. So if you think of this in terms of thermo, which we mechanical engineers like to do a lot, that resistor is going to get really hot really fast and then slowly going to cool off, both naturally through convection, through conduction, through radiation, but also because there's less power being consumed in there. So that's going to be another way that the power is removed, because you have less coming in, you have less you have to give off. And then to tie this full circle, we also have energy at the bottom. So energy is another way of looking at these, and this is the other equation for that, where WT, and this is going to come from your equation sheet that I gave you, WT equals 1 half CVS squared E minus 2T over tau, where tau, again, RC. And this is going to be able to give us our energy decrease. So essentially, you're going to have a large amount of energy. You're going to be able to do a large amount of work, and then decreasing exponentially as you go out through time. So to look at this again, general response of an RC circuit. So the general response is going to include both parts. So we're going to look over here at the same circuit we had before. So this is where it charges up, charges up, charges up, and that's what the picture A is showing. Anytime before t equals 0, it's charging, and that's what B is showing too. And then again, we're showing C once it's already charged. The switch goes, and what happens there? What do we have with this second voltage source? Because you see there's a second voltage source down below. So this changes the one previously because now we have two voltage sources and it's changing between the two. So maybe VS1 is a 9-volt source and VS2 is a 1-volt source. And now we're changing from a 9-volt to a 1-volt. What's going to happen to our capacitor? How is that going to change? Because essentially you have less voltage, which means there's less pushing on that capacitor. So there's less reason to keep charge on there. So the current is going to change through the system. And we do that by looking at the voltage equation by running around essentially KVL for the loop. And that's going to give us our minus 2 VS2 plus IR, because that's the resistor, V equals IR, so that's the V there, plus the V of the capacitor, the voltage drop across the capacitor. And now we can solve this out using the equation I equals CVD dt, and you rearrange terms, and you get the differential equation dV dt plus AV equals B, which is a common form differential equation that we've solved multiple times. It's one of the first ones we solve in class. And A for this differential equation we can substitute in as 1 over RC, and B is our VS2 over RC. And so this gives us our two different sources. R is a constant because it's going to be 10 ohms, I don't know. And our capacitance is a constant. Maybe it's 1 farad capacitor, which is a freaking huge capacitor, but let's just go with 1 ohm and 1 farad. We'll be able to back calculate out what the difference is between these two individual voltage sources and what that looks like. So for our general solution of this, how do we solve this equation? Well, we integrate both sides. This is one way of solving it. There's actually 4 or 5 different ways of solving this, but this is the easiest way. We integrate both sides, and that's going to give us our VEA of t from 0 to t equals B over A E up AT from 0 to t. We can solve that out, and I'm going to let you do the math on your own on this because me speaking about it doesn't help as much. But essentially what we're going to do is as our time approaches infinity, our voltage is going to reduce to B over A equals V Vs2. And so this is going to be interesting when we look at what's happening over the long period of time, because now it's just a relationship of B to A. And remember, B to A is just the difference between those is you have your resistor and capacitor in both of them, but you have your source in B where you don't have the source in A. So you're just going to get Vs out. So that is essentially your steady state, or your long term at the long period of time response. You're going to look at that, and that's going to be at a very long period of time, whatever your voltage there is in the second voltage. So your circuit is essentially going to tune to that second voltage. And that's easy to make sense of, too, because once your circuit, the power flows back from the capacitor backwards, or fills up if it's going from a smaller voltage to a bigger voltage source, you're going to eventually get it to saturate, and that saturation point is going to happen whenever your voltage source is the same as the voltage is the same going into at the top level of the capacitor as your source. And then again, your capacitor is going to open up into an open circuit, and no current is going to flow through here. So logically, this makes a lot of sense if you think about what's happening there as well as solving the math. So here we get a more complex one. Example 510, we're going to determine the capacitor voltage. So this is a 20 mu farad capacitor, and we have a voltage drop over it. And if we look at the left half of the circuit before t equals 0, so this is going to be essentially our charging circuit on the left half. And on the right half, this is going to be our discharging circuit, is the way we think of it. The 45 volts on the right-hand side is part of charging up that capacitor, and essentially you're getting a voltage divider between those two resistors. So that's how you're going to break that 45 into some smaller voltage. I don't know, 20 volts, 30 volts. And again, you can calculate this out. This is 4 to 8, so it's actually a pretty easy calculation. So you're going to get a percentage, though, of that voltage going into your capacitor to charge it up and then back to ground. And that's from negative infinity to 0. So we're going to presume that this capacitor has been on there for a really long period of time, so it's fully charged for that given circuit. Then at t equals 0, we're going to switch it over real fast. And immediately, that capacitor, something is going to happen, because now we have a different source going on that capacitor. And this different source is a 60-volt source. But there's a voltage drop, again, from the 24 to 12 ohms source. And there's also a 2 kilo ohm source before we get to our capacitor, which we didn't have before. So if we look down at figure B, we're going to look at the circuit before and what the Theravin equivalent of that circuit is beforehand. And the Theravin's equivalent circuit is going to be a very simplified answer, because it's going to be one voltage source, one resistor, and one capacitor, which is essentially an open circuit. And this is where Theravin really comes into power, because we can get rid of all those resistors and all the other stuff and mess that's in that left-hand side, and simplify it out to a single voltage and a single resistor. And so that's what we've done in that first half. That left half of the circuit is our Theravin circuit, and that's a 30 volt with a 2.67 kilo ohm resistor and 0 current flowing because the capacitor is charged. When the capacitor is charged, V of 0 minus, or the voltage before 0, is 30 volts. And we know it's 30 volts because that's what our source is. It has to equal our source. And so that is our Theravin equivalent circuit for the left half of the circuit. Now let's do a Theravin equivalent for the right half as soon as we switch it. So as soon as we switch this circuit, we're going to now have a capacitor which is not fully charged, because something is going to happen immediately there. And you are going to have current flowing. And we're also going to have 3 resistors there and a voltage source. So those 3 resistors, we're going to work from the right side to be able to simplify those out, given that voltage source. So you can do a source transformation there. You can use any of the other methods that we've had to be able to simplify those 3 resistors to a single resistor. And when we do that, we're actually going to get, it's a 10 kilo ohm resistor. So the 2 there, the 24, 1 over 24, 1 over 12 is going to be what? 1 over 24, 12, 8. And then you're going to add 2 to it. So that's 8 plus 2 is 10 kilo ohms. And now we have our equivalent Theravin circuit at exactly t equals 0. So we have a 20 mu farad capacitor charged up, and what the voltage drop over that is at any given time. So to continue with example 510, we're going to look at the solution here. So on the top left, we have that Thevenin equivalent circuit that we developed in the previous one, which again, you have your capacitor as an open circuit there because it's fully charged to 30 volts. And that 30 volts is going to give you your V of 0 before any time before t equals 0. So any negative time, any time before you start it. That's your initial condition. Then you're going to have your Thevenin equivalent down below that, which is essentially once you switch the switch, immediately what happens at t is greater than 0. And so at 0, and if you look at the top right, our switch was moved at t equals 0. That's how we're going to be able to calculate out what's going on. So at v of 0 from the negative side, so anything before the switch was switched is going to equal 30 volts. Cool. That's easy for us to add in. And then our v of infinity, so as we go out to infinity, we're going to be able to take that voltage divider, essentially, and then multiply it by 60, and that's going to be 20 volts. Because, again, you have a 20-volt source, so you can have a 20-volt voltage. And that's essentially, as you go out to infinity, that makes total sense because that capacitor is going to charge up, and it's going to become an open circuit, and then that whole top half of the circuit is going to be one single node, and that node is going to be 20 volts. So that's an easy one to understand, too. So that's and then we also can solve for our resistance, our Thevenin resistance, which is going to be, again, you have a voltage divider, you add the two different voltages up, you're going to get, what's that going to be, 8 plus 2, so 10 kilo ohms of resistance. Now we got our tau equals RC, and so tau equals our resistor value, which is 10 kilo ohms, so 10 times 10 to the 3. And then our C equals 20 mu farads, and mu farads is minus 6, so 20 times 10 to the minus 6. So if we multiply that out, that's 10 times 20 times 10 to the third times 10 to the minus 6. Simplify it, that's 0.2 seconds is each unit of tau. And if we substitute the values we obtained for V0 and V infinity, which are our initial case and our infinite case, and tau into the initial equation, we're going to be able to solve for the voltage V of t, and that V of t for our circuit is going to be V of t equals 20 plus 10 e to the minus 5t volts, and that's at any time greater than t equals 0, because remember, at time less than 0, at 0 or smaller, we're just going to have it 30 volts, because that's what we already got from the initial equation from the top left circuit. And then B, if our switch was moved at t equals 3 instead of t equals 0, so that's essentially just changing our time constant, we're going to change our 30 volts, instead of being up to minus 0, it's going to be up to 3 seconds, so we're going to get a piecewise function for that. And then after, we're going to get the same initial v of t, except we're going to do a modifier on that t to be t minus 3, because it's 3 seconds shifted over. Essentially, we've shifted our output there 3 seconds over, and that's all we've done. So for our next example, we're going to look at example 511, a charge and discharge action circuit. So what we've got up here in A is, again, another circuit with a single source, V1, and we've got R1 and R2 and our capacitor. And so what this is going to do is we've got a charge of the circuit from 1 to 2, and then we're going to have a discharge after 10 seconds. So let's read the problem. Given that the switch was moved to position 2 at t equals 0 after it had been in position 1 for a long time. And again, long time implies that that capacitor is fully charged, and that's why they say that. Because if it was only for a second that it was in the other one, or a tenth of a second or a thousandth of a second, that capacitor might not be fully charged, and our math won't work out. So when it says a long time, that means the capacitor is fully charged. And then it returned to a position of 1 at t equals 10 seconds. Determine the voltage response V of t for t equals greater than 0, and evaluate it for V1 equals 20 volts, R1 equals 80 kilo ohms, R2 equals 20 kilo ohms, and C equals 0.25 millifarad. So we got our time segment, which is our first bit. So anything less than 0, we've got from 0 to t to 10 seconds. So again, anything less than t means it's been charging. And then as soon as we switch at t equals 0, it means it's already increasing. So when the switch is in position 2, the resistance of the circuit is R equals R1 plus R2 because those two resistances add. Hence, the time constant during the first time segment is, and it shows you the time constant for that, because tau equals RC, and if you have two resistors, R1 plus R2 equals R equivalent, So we can add those up. And essentially, that's 25 seconds. That's showing that it's going to take 25 seconds to charge for one time constant, and that increases the speed of increases the amount of time it's going to take to charge that capacitor, as opposed to if it did not include one of those. Because again, more resistance means slower charging time, slower discharging time. And then we can go to the equation underneath that and solve through for the differential equation given the different initial conditions. So we have v1 of infinity, which v1 of infinity is whatever v1 is. And then we have our initial condition of v1 of 0 minus v1 of infinity e up t over the tau constant, which is rc. We can solve that out, and that's going to equal v1 of t equals 21 minus e to the minus 0.04 t. And that's going to give us our voltage from 0 to 10 seconds. And if we look graphically at what's happening here, we've got our actual circuit, again, in the top left, A, and we're going to switch that real fast, and then the circuit from 0 to t to 10 seconds, and we're going to look at what's happening there. And then we're going to switch it after 10 seconds. So that's going to be at t equals 10, we're going to flip it and close that circuit off, and that's going to be the second circuit that you see there. So that's essentially what's happening. You're flipping it on for 10 seconds to charge it up, and then you're flipping it off. So how much charge does it get in that 10 seconds? Does it fully charge that capacitor, or is it only partially charged? And then once we determine that, we're going to flip it back and discharge that capacitor. So this is going to give us a different waveform than we looked at before, because everything is going to be changing for the entire duration of this. So if we look down below, we're going to look at the picture first, and then we're going to look at the math for it. But the picture is going to show you that sharp increase of voltage while you're charging, because essentially the circuit starts as uncharged. As soon as you flip that switch, that voltage source is going to start charging that capacitor based on those resistors and how high those resistors are. And then once it gets to that certain point, we're going to flip it, and it's 10 seconds, so it's not fully charged, so we never plateau out. This doesn't show a plateau. It shows a start peak and then a decrease, which is your discharge. And that discharge is going to immediately try to go down, start dropping dropping voltage, because the capacitor is going to essentially be spending its energy going through that resistor and being discharged by the resistor. And eventually at 30 seconds, you're going to get almost back down to 0. And you can see at different times along the way what your voltage is going to be. So at 10 seconds, that's where you're going to have your max. And that makes sense, because 10 seconds is how much time we've let that charge up. So we've never fully charged it, so that's the highest it's ever going to be before we start discharging it immediately. And that's why you get that sharp peak there. And so if we look at the time segment too, so we've already calculated out that left-hand side, so now we're going to look out the right-hand side. So that's going to be at t equals greater than 10 seconds, what happens? And that's the discharge cycle. And we're going to be able to solve that with our initial conditions again, v2 of infinity, and then our v2 of 10 seconds, and then our v2 of infinity, e up minus t minus 10, because 10 seconds shifted over, just like we did in the previous problem. And then we got our tau constant, tau 2. And we're going to do tau 2 equals R2C. We can plug and solve that to get our tau constant. Our tau constant is 5 seconds. So that is then going to be able to plug back in to solve for our peak voltage, 6.59 volts, which is right there on the peak. And I know I'm rushing through this quickly. We're going to go through this pen and paper again later so you can see. But right now I want to talk more about that chart to make sure you get an idea of the concept when I'm solving it later. And then because there's no voltage source present in the R2C circuit, and that doesn't mean there's two R2s, it just means the second RC, the discharge circuit, the charge capacitor will dissipate energy into R2. So that second resistor is going to start taking energy out of the system, and it's going to create a natural response. Because again, there's no other voltage source in there. It's just whatever is left over in that capacitor that can spill out, and once it's gone, it's gone. And so that's going to give us an infinity of V2 of infinity is 0. Because again, we don't have anything to replenish that capacitor. It's just going to run out. And we know it's going to run out. And so that's how we get our 0 out of it. So we can use that concept and plug that into our equation to be able to solve out. And that's going to give us essentially our equation there for the response. 6.59 E up minus 0.2 T minus 10 volt for any time is greater than 10 seconds. And so that way you can plug out anything 20, 30, 40. You're going to see it's going to get closer and closer and closer to 0. Here we're going to look at example 512. And 512 is very similar to the other circuit that we're looking at, except instead of just giving a constant voltage or whatnot, we're going to give a pulse. And that's essentially changing the voltage. So you're going from t equals 0 to t equals 4. You're going to have a pulse of 10 volts and then back to 0. And this is going to change things a little bit, but not too much. We're going to still be able to solve this kind of equation. It's like having two different circuits in one. You have essentially a circuit of 0, and then you have a circuit of the pulse, and then you actually have a circuit of 0. So again, we can look at it very, very similar to the switch circuit. It's like the pulse circuits are very similar to that because essentially the switch, when you switch it up and then back down, is creating a pulse in that circuit, a charging time. So we're actually able to use that exact same example from the previous one to look at what happens if we have a pulse instead of somebody flipping a switch. And so for any time before t equals 0, that's going to be 0 because, again, uh, there's no pulse coming in. There's no DC voltage. It's like having the battery unplugged. Nothing's going to happen. You're not going to get to charge. You're not going to get to charge a circuit with no battery. So as soon as you hit that 0, though, you're going to get that pulse function come out. And that's going to give you a pulse of a certain voltage for a certain period of time, which is exactly like what we just did in the previous one. We switched the switch on and let it charge up. It was like there was a battery there. And then we switched it off again and let it discharge because then there's no battery there. So that's what's going to happen here is we're going to switch the switch on, essentially, with the pulse. And it's going to be a 10-volt signal coming in, charging that capacitor up through that resistor. And after our 4 seconds, we're going to turn it off. And we're going to see what happens to that capacitor, what the system looks like. So we're going to break that down into two different circuits. So for the first one, that's picture B, you're going to have the charging part of the circuit, which is exactly what we did before. You're going to charge it up, and that's going to be 10-volt source for 4 seconds. And remember, the seconds is going to be important because you got your tau and your time over your tau, and your tau is RC, so time over RC. That's going to give you your time constant. And so that's your charging part of the circuit. And then you're going to flip to part C after 4 seconds, which you're going to have a discharging part. Because if you have a 0 voltage source, that voltage source is just going to act like a wire. And you're going to have current come backwards through that circuit to discharge and release some of the charge that's on that capacitor to bring it back down to normal. And so what that's going to look like is we solve the math through. And again, you can solve through this, but it's exactly the same as we did before. We're going to have that picture down in the bottom right. You're going to have your forced response, and the forced response means that you have some kind of voltage source in there, and the voltage source is that pulse, and that pulse is going to increase sharply your voltage up to 4 seconds because that's how long the pulse is. 10 volts at 4 seconds, so all the way from 0 to 4, it's going to get higher and higher and higher. And then as soon as that pulse is shut off, that capacitor is going to start discharging immediately some of that voltage, and that's going to discharge through the natural response of the system. And that's going to discharge all the way down to 0, and the time constant for that discharge is going to be given based on the resistor and the capacitor value. And if you look at the math above it, this is almost identical to the last one we did in 511, and I'll show you this one on paper too to write it out, and that way we have a little bit more understanding and explanation of how they're working. But from a conceptual idea, I want you to see that the pulse is acting like a switch almost, where you're charging it up, and then as soon as the pulse is off, that capacitor is discharging. And that graph that you see with that sharp tooth coming up and then that slow curve coming down is essentially your response. So you can do some interesting signal things with this too, because again, a pulse is a signal. It is a form of a signal. It's an on-off and an on-off. And if you want to change that pulse into some smoother signal, we're essentially smoothing that down now into a spike and then a response, that natural response line. So here we're going to look at the RC as a first order response in time. And this is again showing you kind of how these signals relate. So if we look at that top line, we're going to get essentially a step response from 0 to V. And that step response up is the first part of that impulse that we looked at in the previous one. So if you look at the little tiny picture in the top right, you can see the step response of 1 volt, essentially. So it's 0 before time equals 0, and then anything above it jumps up immediately at 0 to whatever the voltage is and holds that voltage. Likewise, you have a step down as well in the one underneath that. At any time less than 0, you have, I don't know, 1 volt, 5 volts, and then immediately at t equals 0, you're shutting that signal off. And the ordinary differential equation for that is shown there, tau dy dt plus y equals k of x, with your time constant tau equals rc and your static gain k equals 1. And these are, again, the differential equations in order to solve these. So your v of c of time equals a plus b e up minus t over tau, and that minus t over tau is giving you your time constant, essentially. You're taking the time over your time constant. And this a and b, again, we explained on previous slides on how to calculate that. If you look down at the bottom, you have our individual our V's for a resistor, capacitor, and current. So V equals IR for resistor. We've already done that. For our capacitor, Q equals CV. And then for current, we have IC equals dQ dt. And so if we look at the response to a positive step, which is the charging section, and the response to a negative step, which is the discharging section, and we solve those, what we're going to start to get to that pulse function is the applied voltage on the capacitor. So if we look at the picture in the bottom right, this should start showing you what you can start to do with these circuits and what they're doing to a signals level perspective. So if we look at the blue signal is essentially that step function, that high charge up and then the high discharge real fast. So that's your step up and your step down, and that's creating that pulse going across there. What our resistor and capacitor in the circuit are doing is they're smoothing those sharp changes. They're smoothing those impulses. So that step up, that sharp increase, is actually smoothed out slowly in order to get to the top. And then same with that sharp decrease, that's smoothed out slowly to get to the bottom. And there's a lot of times in circuits and filtering of circuits where we want to smooth the circuits out because maybe we have a really fast, sharp impulse up and down, and we don't really want that full impulse. We want to get rid of that because that's not part of the signal we want. Maybe that's somebody tapping on the sensor or some small amount of static. Hopefully not, because usually static breaks a lot of our electronics, but maybe it's a static for some analog circuit. And so we want to smooth out those extraneous signals. And that's the filter circuit. Essentially, at a most basic level, we're filtering those sharp changes out to make them smoother. We could do a lot of really cool stuff with this once we start being able to filter out selective frequencies or filter out selective impulses. We can start to be able to shape our signals. So again, if you have a speaker system playing music in the background and you have a subwoofer, you don't want to put a lot of high frequencies through that subwoofer because the subwoofer is designed especially to produce low frequency bass sounds. So throwing high frequency through it, A, wouldn't sound good, and B, is a waste as a subwoofer. You buy it to produce those larger, deeper sounds. And so maybe you want a low pass filter. It lets low frequencies pass but blocks high frequency filters. And again, that's what we're doing kind of down here in this picture. We're smoothing the signal out to let certain frequencies or certain changes through. So the next bit of this is to look at the response to a series of steps. So previously in that last one, we looked at a single step in the smoothing there. And at the previous one of that, we looked at a single impulse in and out. And then before that, we looked at a switch turning on and off. And before that, we looked at no switch, or a switch just turning on. So now we're going to start to look at a series of pulses a series of steps in order to build some complexity to our design. So this is a fun problem. We're going to look at a series of pulses. And why we're doing pulses is because pulses are a little bit more like frequencies that we might look at. So you could actually break voice down into a set of pulses. It wouldn't sound perfectly right. If you did a really high sampling rate, you could get those pulses to sound closer to a voice. But it's a step in the right direction to building complexity. So that's why we're looking at a bunch of pulses that don't quite line up or they're not periodic. These look like random pulses to me. So in this example, we have 6 different pulses here at 6 different levels. Essentially, you can think of that as your voltage in or your voltage out. Let's say voltage in. And these 6 individual pulses are happening, and we're gonna look at an unknown circuit. So we're gonna look at a circuit that we've built and what the output of that is. And so this is going to be our input. We're going to look at the output, and then we're going to be able to back calculate our RC value. We're going to be able to see what that might be and take a gander at that based upon the output and comparing the output to the input. this is another kind of fun way, again, graphically of looking at these. So this is our input. Next slide is going to be our output. Here we have our output overlaid across. So this is the voltage measured across a capacitor in response to the input. So essentially we put a multimeter in front and behind the capacitor, and we've just measured what's happened as these pulses have gone through the system. You can see you get this really funky, like, shark fin pattern coming up and down the whole way across. And it's significantly smoothed out a lot of those sharp boxes. You still got some points in there, but it's significantly smoother and more averaged out than we had before. So this is our output. So now we're going to be able to look at the equation for this response. So the equation for this response is given here, where Vc is the charge in the capacitor with respect to time, Vs the step voltage, Ti the start time of the step, Vc is the voltage across the capacitor, and tau is the time constant, Rc, like we usually use. And we're going to be able to come back to the equation, and each of these values can be read off the graph above directly with the exception of the time constant. And we can find the time constant from any of the individual step responses by knowing that t minus ti equals tau, because the exponential becomes e to the minus 1, because we want to get rid of it. So that is the easiest way that we can pull back data from the input versus the output. And again, the output is the voltage measured across the capacitor. But this is showing how you get the equation from that input-output and the smoothing there. So, in order to calculate everything out, we're going to look first at step 1. So, step 1 is that first impulse. So what we're going to do is we're going to find the time constant tau using the step 1. So that first step 1, we're just going to lock everything out of there. We're going to solve this piece by piece by piece. So step 1, we're going to look where the input starts, and it starts at 0 volts, and it starts at 0 time, and it steps up to 2 volts immediately. So that's the brown one. That's your step function. It's from 0 to 2 immediately, pretty much. Then we know that t minus ti equals tau. We can substitute in for the expression of that, where e of minus ti over tau, e up minus 1. And that's going to give us, essentially, you have an immediate step function there, and that's why we want the e to the minus t. We have an immediate function. So now we can substitute in for that, and we're going to be able to get v of c of t for those given conditions, substitute in the 0 and the 2, and we're going to be able to get out 1.26 volts, and that's going to be 1.26 is going to happen at the given time that we're looking at. So what is the given time we're looking at? Well, we can solve that in to get our time constant, and that's going to give us, solving down, a 0.5 seconds, and that is our individual time constant for that. So that's how we can convert equation-wise what those points are and what the output is. So this works for every step. We're going to try this again using step 5. So you go right across each one of these pulse steps, and that's going to be able to solve. And we kept the equation down there below just so that you have it to be able to solve through it. So to go to step 5, this is the decreasing. We're discharging here. We have a pulse that's going from 3 to 1 immediately, and we're going to be able to solve this out. So our Vs is going to be 1 volts. And then at the start of the step, Ti equals 5 seconds. And then our initial voltage across the capacitor is Vc times 5, so 2.8 volts. And then we're going to be able to solve through that, E up minus T minus 5 over tau. Plug that in, and you're going to get 1.7 volts. And so we're going to be able to compare that down. 1.7, we're going to look at that blue line and drop directly down to be able to grab our time constant, or now our tau constant. And at 1.7 volts, our tau is 5.5 seconds. So we're going to have tau equals 0.5 seconds. And we can do this for every single step across for step 3. And I'll leave this up that you can kind of work through at your own pace to be able to see. But at the end, we're going to be able to generate the equation from this. So now that we have the time constant, we can have the complete first order response equation. And if you look, the time constant of 0.5 is in the denominator in that exponential. So E up minus T minus Ti divided by 0.5t. The T minus Ti is the shifting function, and the 0.5t is your tau, or your Rc, or your constant between the two. So this is defining the voltage across the capacitor, Vc of t at any time t. So as long as you can determine the initial conditions for each step. So as long as you can determine the time initial, the voltage source, and the VC of the time initial, you're going to be able to pull out from those the time constant and the tau, and you're going to be able to solve that equation for input versus output. And if we do that at each one of these points, this just is the solution set and how the solution set was developed. So Ti from 0 at Vs of 2 volts, and you can is going to give us, we use a step of Vc of Ti equals 0, and we can calculate for the Vc of 1, and that's going to be 1.7 volts, and that's the top peak. And we can calculate these out for each one of these, and that's going to give us essentially our peaks of our individual outputs there. And you could do this in Excel, you could do this by hand, you could plug this into your calculator into tables, however you want to be able to get this kind of output. So now that we've kind of walked through the general response of the RC circuit, we're going to look at the RL circuit. And a lot of what we've already used can be applied here concept-wise to the RL. The RL is just slightly different, not too much. But if we look at circuit A in the top, we have two different switches. We have the switch 1 and switch 2, S1, S2. And at the t equals 0, we're going to flip those switches from 1 to 2. So let's just look at what's happening here at t equals 0. So we've got current coming out of the source 1, IS1. Sneeze. Nope. Current coming out of IS1, going around the top of the loop, and it's going all the way over to the right through that resistor and through that inductor there, the R and the L. Hey! Excuse me. And the L is essentially, we can look at what the voltage drop over that. The voltage drop over the resistor is easy, V equals IR. The voltage drop over the L is slightly different than we've looked at before. And VL equals L IL dt. So that's going to be the change in current over time. So like capacitors were to voltage, inductors are to current. So an inductor, when it's turned off, is going to be able to provide a little current to the system for a short amount of time as that magnetic field collapses. So in that first bit, as long as we've had the system plugged in for a while, that inductor is going to be fully saturated with the magnetic field. And so that's filled up. Essentially, it's held as much magnetic field as it can. At B, we have that initial condition that t equals 0 from the minus side. So this is all the way up to the absolute minimum, the absolute 0 of the t. So that's going to look at what's happening there is exactly what I said before. Once your inductor is fully charged, it just acts as a short circuit. So you can pull the inductor out and just draw it as a line there, and that's all it is. There is no change in voltage there. It's 0. It's just a line. So all of that current is going to go through that line and not through the resistor that's there to the left of it. Everything goes through the inductor because, again, it's just a wire, a metal wire that's going through, so you're going to be able to short through that piece of the circuit. So that's why we have our VL of 0 from the minus side equals 0. There's no voltage drop, and essentially you have a short circuit right there. Now, as soon as those field lines start building up, you're going to get that magnetic field starting to build up. And so some of that current there from I2 is going to flow up from I2 and split, because you have a current divider there, into IL and IR. And the split is going to change, the response. You're going to get the natural response there. And as that magnetic field charges and discharges, you're going to be able to see what that natural response is until it reaches equilibrium again. And once it reaches equilibrium again, we could draw that as a short circuit, and you're going to have all the current flowing through there. So we look over at our equations on the other side, and this is going to be able to give us our switch action at t equals 0. So that's going to be IL of t equals IL of infinity. So what happens when you grab the current as it goes out to infinity? What happens when you add the current at 0 minus the current of the inductor at infinity times E up minus t over tau. And so this is going to give us our Our time constant tau equals our time constant tau equals L over R. So remember, for capacitor circuits, tau equals 1 over RC. For inductor circuits, for RL circuits, tau equals L over R. So it's a little different there to be able to solve. And below, you're going to see your initial conditions too. So this is example 513, and here we're going to look at two RL branches, resistor-inductor branches. So the problem states that having been in position 1 for a long time, which means it's fully saturated current-wise, and there's a large magnetic field built up in that inductor, the single-pole double-throw switch in figures below was moved to position 2 at t equals 0. Determine I1, I2, I3 for t is greater than 0, given that Vs, the source voltage, is 9.6, Rs equals 4 kiloohms, R1 6, R2 12, our inductor is 1.2 henries, and our other inductor is 0.36 henries. So, let's look at A. In A, we have a voltage source with two resistors, and actually we have a voltage source with three resistors, because if we look at that circuit, the voltage source is going to push some of that voltage out through that resistor, and then it's going to split down I1 and then I2. Nothing's going to happen I3 because that's an open circuit, but it's definitely going to split from I1, I2. So that's going to charge both of those inductors up. And it's going to split the charge between those, depending on the values of resistors and the inductors. But once we flip it to 2, let's look at what happens there. At 2, we have, again, two different inductors that are going to feed back into that I3. So both of those inductors are going to give some current back to I3. So at the very first bit of this, let's break it down into time chunks. So the very first time chunk is before 0. And at before 0, we know that these inductors are fully charged, are fully saturated. The magnetic fields are high as they're going to get for that voltage source. And so we can draw them as shorts in the circuit. And that's what we've done in red there for L1 and L2. We've drawn them as shorts, and we know that the current flowing out of that voltage source through that resistor is going to split from I1 and I2. And we can calculate this all out right now, because it's essentially just a voltage source with three different resistors. And so we could calculate out what our initial conditions are. So if we look at node V right there, we're going to do KCL there. And we're going to add up at that node, we're going to add up what our currents in and our currents out are, because remember, current in has to equal current out. And that's going to give us I, V equals IR, so I plus I plus I. And that's the same thing that we did before in nodal analysis. So we're going to be able to solve that through to be able to determine what the V is. What is the voltage at that node? And the voltage at that node, if we solve through the math that's there, it's going to be 4.8 volts. And so we can determine what our initial currents, I1 of 0 and I2 at 0, are given by plugging that in. And we can plug in, it's V over R1, and we have our 4.8 over our R1, so we know what the current going through I1 is, and that's going to be 0.8 milliamps. And I2, we're going to do the same thing, it's going to be 0.4 milliamps. And that makes sense because of the values of the resistors, too. R1 is going to be half the value of R2, and that's going to be able to help us out to make sure that we know exactly what our currents are, because I2 is going to be half the value of I1. So that solves out our initial currents. After this, we're going to look at what happens at t equals 0 and after t equals 0. So at t equals 0, we're going to simplify the rest of the circuit and remove all that other, the voltage source and the resistor there. And our circuit's going to look like this in the top left-hand side, where we have a current coming out and splitting into I1 and I2, going through the two resistors and then the two inductors. So those two inductors have stored some current, so they're going to send some current back through the system. And if we look at the bottom picture, we have what the plots of I1, I2, and I3 are. So I3, of course, is going to have the highest value when we initially start, because there's going to be an addition of the currents between I1 and I2 based on that resistors there too. So the resistor is going to kind of even it out a bit as well, because the resistors are where that energy is being dissipated, and so the values of those are going to change our current versus time. And so we look at that, and we're going to get our max peak at 1.2 amps, 1.2 milliamps. So let's look at how we calculated all these out. So at t equals 0, we're going to be able to plug in those initial conditions into our current equation for our L circuits. And the initial equation of I1 at infinity, our current at infinity for an inductor, is going to be what? 0. And then our initial current I1 at 0 minus our I1 infinity is going to be able to solve and plug in for that to be able to get our 0.8. Because remember, we got that on our previous slide. 0.8 for the I1, and then we're going to have 0.4 for the I2. So essentially, we're, in the absolute shortest, we're multiplying this by the E up minus T over tau 1. And that is going to give us our equations there for current versus time, instead of just having current at a set time, like current at just 0. So those are our initial conditions, and now we're going to go down to where tau 1 and tau 2 are the time constants of the two RL circuits. So remember, we use our equation tau equals L over R to pull out that time constant, and we're going to get it there. Our time constant is going to be 2 times 10 to the minus 4th for tau 1, our first inductor, and then for tau 2, it's 3 times 10 to the minus 5. And we're also going to be able to add them together, because remember, currents add. Currents into a node equal current out of a node. So I3 is going to be the sum of these two individual current versus times. The 0.8 E up minus T over tau 1, which is we've already calculated out, and the 0.4 E up minus T over tau 2, which we've already calculated out. Here we're going to look at RC op-amp circuits. So we ignored before two of the most critical op-amp circuits that we've got, which are the integrator and the differentiator. And the integrator allows us to perform integration mathematically using an op-amp. And we skipped it before because we didn't have RC circuits yet, but now we can actually kind of look at what's happening in an RC circuit. So we know a capacitor takes a little bit of time to charge, and we know the equation for a capacitor um, versus for current is going to involve the integral in order to get our voltage. Our voltage is going to be, if you look in the blue box in the bottom, voltage out is going to be 1 over RC, the integral of 0 t to t, VI dt plus V out initial t. So this is the integrator circuit for an op-amp, and we can use this to integrate a number, same as a mathematical function that we use to sum numbers or subtract numbers with the differentiator, or sum them with the adder, or invert them with the inverting op-amp, or multiply them by a gain factor with a normal amplifier, or an inverting or non-inverting amplifier. So now we're going to be able to do integration with an op-amp. We've got many, many examples of this coming up, but I do want to point out here a couple of small things. Essentially, because we have that integrator in the voltage, because op-amps produce the voltage out. That's the thing we look at with op-amps. We are able to produce that integration through the voltage of the op-amp coming from the V out. And the feedback is going to be going through that capacitor. And again, the feedback means as the circuit goes on, as the circuit charges up, we're essentially going to be pressing less and less charge against those panels. There's going to be less and less charge. There's going to be more charge, less current flowing through. So that's where the feedback comes through. So we're going to look at these and calculate a few of these out in a minute. Here we're going to look at our first calculation for this. We have a square wave signal coming in, and that's shown in A. That's a pretty standard square wave signal. 0 up to 3, down to minus 3, up to 3, down to minus 3. So all intents and purposes, a very standard input for a square wave. You could make this with your 555 timer. So what the question is asking, a square wave signal is applied to the input of an ideal integrator circuit with an initial capacitor voltage at 0. So that means it's going to start, the capacitor isn't going to start charged. And we're going to have R equals 200 kiloohms, C equals 2.5 mu farads. determine the waveform of the corresponding output voltage for an amp with the VCC of 14 volts and B a VCC of 9 volts. So what we're going to do here is going to be able to plug some of this stuff in to be able to calculate out our output and what that looks like. So the scaling factor, again, we're going to use is the scaling factor for time. Remember, tau is going to be 1 over RC, and that's going to be our scaling factor of minus 2 seconds to the minus 1. And then we're going to look at the integration there. So the integration V out equals minus 2, which is the scaling factor, times the integral of VI dt. And we can look at each one of those input signals, because remember, we can put each one of those step impulses in. Each one of those pulses can be integrated. And we're going to be able to pull out from different time periods what the output is. So again, from any negative infinity to 0, we've got 0. That part's easy. And that's going to be 0 at the voltage the whole way through. So now we're going to look at from 0 to 2 seconds. And from 0 to 2 seconds, we integrate that. And it's 3, so we're going to do 0 to t of 3, and that's going to be 3 times 2, so 6, so minus 6 carries the minus sign over 2. So that's 6t volts. And so as long as we're going through time, you're going to multiply minus 6 by t, and that's going to give us a ramp function down, which makes sense. It's what we're looking for. So if we look at the integral for that step function, we're going to get those ramps. So from 0 to 2, it's going to go as a slope minus 12 down and 2 over, and that's how we get our first slope down in picture B. And now we can repeat this again and again for each one of those other ones. So you're going to get a negative and a negative, which is going to give you a positive slope up from 2 to 4. You're going to get a negative times a positive, so you're going to get a minus slope down from 4 onto 6. And so we've done that with the output of 14 volts in B. We can do the exact same thing with the 9 volts. Now what happens there, we have a little difference because we're getting beyond the power that the op-amp has. So if the op-amp only has 9 volts of power applied to it, the max signal it can produce is 9 volts. So what happens when you go beyond 9? Well, you just clip the output. The output becomes flat. And so now we get a really kind of cool, complex trapezoidal signal, which is interesting to come out of it. And that happens, again, because our op-amp is at 9 volts. Now, if our op-amp was 12 volts or 50 volts, we wouldn't see that. If our op-amp was 6 volts, plus or minus 6, like the MCP6004 op-amps that we have from Microchip, you're going to clip that output even higher. So it's going to be up higher. At that minus 6 volts, you're going to go flat right over there. So it's going to be probably from time t equals 1 to t equals 3 that you're going to have your flat peak, and there's going to be no slant in there. Another op-amp circuit that's very interesting is the ideal differentiator, and this is similar to the integrator, except the position of the capacitor is different. So in the integrator, we have the capacitor in the feedback loop. With the differentiator, we have the capacitor between the signal in and the negative feedback, before the node of the negative feedback. So IC for this, again, same equation we've had, IC equals C dVi dt, IR equals V equals IR, same equation there, IC equals minus IR, and we're able to solve our V out, which is very simple. Our V out equals minus RC dVi dt. So it's going to take again, the derivative of that function there, Vi dt. So here we have a pulse response for 516, and we're going to look at what that does. So we have a pulse coming into it, and that pulse is going to travel up through R1, and we have a node there where it's going to split between a resistor and a capacitor as well. And what we're going to have on the bottom is our output. So if our input is just a pulse, our output is going to be essentially charging, and the charging is negative, because remember, look at the capacitor's direction, how the circuit is charging. You're going to have that charge go up negative to minus 8 volts, increasing to minus 8. And then you're going to have, as soon as that pulse is over, the capacitor is going to start discharging. And it's going to go back to 0, because 0 is a discharge capacitor. It's an empty capacitor. And so that's where you get the capacitor discharge curve from as well. 518 here, we're going to look at a differential equation solver. And so here we're going to start using op-amps to solve differential equations, which is kind of a cool idea on its own. Op-amps are little computers. When you stack them together, they can solve really complex problems. So why not solve a differential equation that's shown for us? So here we got a differential equation, d2v over dt2 plus 8 dv dt plus 2v equals 4 vst, where vs of t is a sinusoidal source given by 3t 200t u of t. So we're going to first get our solution set for that. And to plug through for our solution set, we're going to get v equals minus 1/2 v double prime minus 4v prime plus 2vs of t. And then we're going to also plug in our signal into that because we're given vs of t. So that's going to be our equation there below. And now we're going to work at making that equation with op amps. So let's look at that equation. What do we have there? Well, we have a differentiator, two differentiators, because we have two derivatives. We're going to have one differentiator because we have one derivative. And then we have the input function, which is going to be our sine of 200t. And we have to add each of those together. Actually, we have to subtract one and add the other. So we're going to start with our signal. Look down at the bottom where the signal's coming in. At t equals 0, we're going to let that sinusoidal signal come in. It's going to come up through the resistor. It's going to go to that summing point, and some of that's going to feed back into our differentiator. And that's going to feed forward into our second differentiator. And that's how we get our two different derivatives there. We're also going to look at summing at the summing point there, because that's going to be our positive. But because we have one negative, that's why we're going to have to do our inverter, because you're going to have to multiply that answer by a negative value, so you're going to have to invert it to a negative. And it's again going to go to our summer, and then our summer to our output. So this is going to take a little bit longer. I'm going to try to print this one out. We're going to talk about it piece by piece by piece to try to walk through why this works. But for now, try to see what that you can use these op amps, 4 op amps, to do a complex function like this with two derivatives, double prime, a single prime, and a weird signal coming into it too, in order to get an output. So in conclusion here, we have our summary slide, and this again is the really important slide for everything that we've covered so far. Just to walk through things kind of quickly, we have our unit step function, which is the step up, step down. We have our time shifted step function. That's where if you wait a second or two and then have it step up, what that looks like equation-wise. We have our ramp function, which gives our slope. We have a time shifted ramp function where we can shift our ramp left to right via time. So add 3 seconds or subtract 3 seconds. We have our unit rectangular pulse function, and essentially that's a piecewise function for before the pulse happens, while the pulse is happening, and after the pulse happens. We have our current equation for capacitor, our voltage equation for capacitor, and our stored energy in electrical capacitor, which is W equals 1/2 C V squared. And we also have our capacitance. If we wanted to make a capacitor ourselves, we can look that the capacitor is the permeability constant times the area divided by the distance. We also have inductors here, and the voltage through an inductor over time is V equals L di dt. We have our current over time, which is going to include the integral. And then we have our stored magnetic energy in an inductor, which is 1/2 Li squared. We also have a solenoid, which I did not go through the slides about, but solenoids are pretty cool. This is how you can make inductance, and L is inductance. You can make it essentially you can make one by changing the coils of wire, and N is the coils change. So the more coils you have, that increases it to a power of 2, your inductance. So that's an important one too. We have our series RC circuit response with a sudden change at t equals 0. So that's the series RC, and the equations for that. That's your essentially your differential equation looking at the different parts of it with initial conditions based on 0, and then what happens at infinity. We have our parallel RC RL circuit response, and that's going to show, again, with initial conditions of current of infinity, and then at time is infinity, excuse me, and time equals 0. And then we also have our two different op amp circuits, which are op amp integrator and our op amp differentiator, which we can add and subtract together to create more complex integration and differentiation equations. So this is a huge amount of information in this chapter. That's why I broke it into 3-hour-long videos instead of one class period to do it. So I hope this helps. I'm going to try to do some problems later tonight so that you can have some of these worked out so you can see problems. I'll give you a problem set from the book as well so that we can work through those and you can learn through those as well. But for now, I'm going to sign off and good luck with this.